Today's topic is conservation of energy, Bernoulli's equation. So I'm going to discuss the principles of conservation of energy as it applies to the field of fluid mechanics, and we are going to take a look at Bernoulli's equation and how it can be derived, and then we would solve a few problems, and we leave it at that. So let's get started. Remember this wonderful system of flow through a pipe that we have visited in the past. I'm going to use the same figure again, makes it easier for you to refer to. From the physics, you probably learned that energy can be either created nor destroyed. So we cannot really create energy, or we cannot really destroy it, but what we can do is we can transform it from one form to another, and that is the principle of the conservation of energy from physics. And this statement that I highlighted here in red is actually the law of conservation of energy. It is a universal law that is applied to every field of engineering that you can imagine. So let's talk about Bernoulli equation and how we can apply these principles of conservation of energy to a fluid flow and derive an equation for that could describe the flow of the fluid, but using energy principles. There are three types of energy that's involved in a typical flow: potential energy, kinetic energy, and flow energy. Potential energy, of course, if we have a pipe that is elevated from a reference level due to its elevation, there will be a potential energy. We show that as PE equal to W times Z. Z is the distance from the reference level, and W is the weight of the element. So that is the potential energy for any fluid. There's also kinetic energy, and that is caused due to the velocity of the fluid. The kinetic energy is shown here as KE. It's W V squared divided by 2G. V is the velocity of the fluid. W is the weight of the element, and G is the G that we commonly use. The G that's pretty common, the G force. And the flow energy is also another types of energy that's involved with the flow of a liquid or a fluid. Of course, fluid could also be gases. This is called pressure energy sometimes, or flow work. This represents the amount of work that is required to move the fluid from one point to another. Of course, there will be some resistance. Again, this resistance could be coming from different sources. We call that the pressure that is caused by the flow of a fluid, and we abbreviate that as Fe, and that is Wp divided by gamma. I'm going to shortly look at all these energies separately and how we can actually combine it. Note that this is applied to an element of the fluid as shown on this figure down here. That element of the fluid has a pressure, has a velocity, and it is at a level reference. It's above a reference level by a distance z. So as you can see in the figure, again, this is the magnification of what you've already seen in the previous slide. In this case, we are looking at an element of a fluid, and we try to move that by a length L, or by distance L. This is equal. This is this L equals to the length of the element. So we are trying to move this element by using forces from the original point that is shown here to the dotted line that is shown down here. That is the distance, moving it by a distance of L. In that case, work that's done should be P times A times L. P is the pressure, A is the area of the element of fluid, and then we multiply that by a distance L, and A times L is nothing by the volume, but the volume of the element. So A times L is V. In this case, we can replace the weight of the element, W. As we know, the weight is W is gamma by V, and gamma in this case is the specific weight of fluid. Then the volume of the element would be W divided by Y, and we have from this case, this is not Y, this is actually gamma here. Okay, so make sure you guys note this. Okay, all right, so it's really V is W divided by gamma and not Y. In this case, the work would be P times V, which is PW divided by gamma. If we replace V by W divided by gamma, and as such, FE, fluid energy, would be WP divided by gamma. So it's important to note all these symbols and go through all of these derivations step by step. So, as we already discussed, the sum of the energies would be fluid energy, potential energy, and kinetic energy. If we sum them up, we're going to get the total amount of energy that passed by the element of a fluid. As such, we are going to add the terms for Fe as Wp divided by gamma, plus Pe would be Wz plus Wv squared divided by 2g. And note that each term in this equation is in the unit of energy. That's a good verification for us. And in U.S. customary system is a pound foot or foot pound, and in SI units it's Newton a meter. Now let's go back to our wonderful system that I have shown you at the beginning of this lecture. And that is, we are looking at the change in energy from point 1 to point 2, assuming that at point 1 we have V1 and we have a particular pressure P1, and at point 2 we have the velocity of fluid at V2 and with the pressure P2. And this is the same fluid that is going from point 1 to 2. The distance or the reference level is set down here, and the distance of point 1 from the reference level, from the set reference level would be Z sub 1, and from the set reference level 2 would be Z sub 2. So we are considering an element of the fluid and that moves from section 1 to section 2. The values of P, Z, and V are different at two sections. At section 1, total energy using the energy equation that we just developed up here would be simply I substitute the pressure at that particular point. The gamma for the liquid is the same because we're talking about the same liquid. W is the same, we're talking about the same liquid, and G is the same. So the difference would be a P1, a Z1, and V sub 1. And at point 2, again, I'm going to substitute the pressure at point 2, z of point 2, and the velocity of point 2. So at E1, at point 1, E sub 1 would be this term here that I'm just check marking, and at point 2, E2 would be the energy. So what we are trying to do is we are trying to change how much this energy would be different. So we're equating E1 to E2 because actually there is no difference in the energy. What happens that we already discussed according to the principles of conservation of energy, that the energy can be transformed from one form to another, but it can never be destroyed, it can never be created. What we do really in the field of energy as well is we are creating energy by transforming it from one form to another. So really the term creating energy is not the right term to use in engineering. It's the transformation from one form to the other that is the more correct. So if we don't add any energy to this system, or we assume there is no head loss, or there is no loss in the system, we're going to define all these terms later. If we assume that there is no energy added to the fluid, and there is no energy loss between section and 1 and 2, and then we can go ahead and apply the principle of conservation of energy, and it shows that the E1, E sub 1 must be equal to E sub 2. And we already have the terms for E sub 1. Down here we show that. For E sub 2, we have these terms. We equate them. We drop the W terms out. These are the common terms that could be factored out from each side of the equation and dropped out from both sides of the equation. So P sub 1 divided by gamma plus Z sub 1 plus VV sub 1 squared divided by 2G would be equal to this equation that you see here. And this is our wonderful Bernoulli equation, the equation that everybody will have been waiting for. This is the wonderful Bernoulli equation that I'm going to enclose it by red. So this equation is called the wonderful Bernoulli equation. Of course, wonderful is in parentheses depending on how much you like working with equations and how much you like fluid mechanics. And I'm sure you all would love fluid mechanics by now, right? So let's take a closer look at Bernoulli's equation. Each term in Bernoulli's equation is one of the form of the energy possessed by the fluid per unit weight of fluid flowing in the system, right? Okay, so the units for each term are energy per unit weight. Again, in SI system, the unit would be Newton meter, and the per Newton, and the US customer unit would be pound foot per pound. Now, let's take a closer look at the Bernoulli equation and what do we call each of these terms. Okay, so if we assume that each term represent what we call the head, then P over gamma is called the pressure head, Z is called the elevation head, and V squared divided by 2G is called the velocity head. That is the contribution of pressure due to each of these different parameters. The sum of these three terms is called the total head, which I'm sure you've heard in for those that have dealt with pressure and fluid mechanics in the past. And again, they are shown in this case for the case of Z1. The total head is the elevation head, that is from the reference point. How far is point 1 from the reference level? That is the elevation head, and that is due to the potential energy. And the two other terms are due to the kinetic energy. One is the pressure head, and the other one is the velocity head. and the pressure head would be the the terms that we've already defined. One is due to the kinetic, the other one is due to the motion of the fluid itself. So from here, of course, the velocity head at section 2 will be less than the velocity head at section 1 because of the shape of the pipe and because, as you can see, as demonstrated by this figure, we can see that according to the continuity equation, A1 V1 would be A sub 2 V sub 2, and from here we can simply take V sub 2, and we can see in this case, because the cross-sectional area of the pipe at the 2 is larger, that is A sub 2 is greater than A sub 1. Remember that we also defined Q previously, then V sub 2 must be less than V sub 1. And because the velocity is squared, as you can see in the terms of V2 squared divided by 2G versus V sub 1 squared divided by 2G, and then V sub 2 squared divided by 2G is much less than V sub 1 divided by V sub 1 squared divided by 2G, and so on. So in summary, let's take a look at summary of what we've discussed so far. And that is Bernoulli's equation accounts for the changes in elevation head, pressure head, and velocity head between the points in a fluid system. Just imagine that the figure that I just showed you, have a mental picture of that. It is assumed that there are no energy losses or addition between the 2 points, so that the total head remains constant. These are very important when we apply Bernoulli's equations. If these conditions are not met, we cannot apply Bernoulli's equation. Shortly, I'm going to talk to you about the limitation of Bernoulli's equation. Note that when we write a Bernoulli equation, pressures at the 2 reference points both be expressed as absolute pressure or both as a gauge pressure. Otherwise, you're going to run into problems. You cannot have one in gauge, the other one in absolute. You need to express them in the same type of a pressure, either absolute or gauge. So some of the restrictions of a Bernoulli equation is of special attention. It is important to realize that Bernoulli equation is only valid for incompressible fluids, because the specific weight of the fluid is assumed to be the same at the 2 sections of interest. If the specific weight of the fluid changes, then we cannot apply Bernoulli equation for those 2 points. So please keep the principles that we drive the Bernoulli equation based on in mind. There can be no mechanical devices between the 2 sections. That is pumps, any kind of a suction device, any other device that would either add the energy or remove the energy from the system. Again, when we are saying add or removing, we're talking about conversion of energy from one form to another. There can be no heat transferred into or out of the fluid. That is also the violation of the principles in which we derive Bernoulli equation on, and that is heat is a form of energy. If we take heat out or heat in, that means we are changing the equilibrium of the system. There can be no energy loss due to friction. So these are the assumptions, 4 main assumptions that we would use to apply Bernoulli's equation. Of course, in reality, there will be no system that meets all these assumptions. So there are many systems for which we can apply this. We can have some error. Error could be negligible. There are also situations in which, or systems in which we apply this, and we're going to get larger error. We're going to take a look at all those. Let's take a look at the application of Bernoulli equation. I wrote these out here according to your book. However, I think it's better if we go over that in the form of an example, a numerical example, rather than just writing it out. I think we need to apply it and to be able to make sense out of these procedures. So I'm going to skip these and take a look at some of the applications of Bernoulli equation for tanks, reservoirs, nozzles, and so on. So if you can concentrate on this image that is shown here, and this is a fluid flow system. It's a siphon that draws fluid from a tank or reservoir, if you will, and deliver it through a nozzle at the end of the pipe that is point F, okay, down here, okay. And point A, the pressure would be 0 because that is the surface of the tank, and this is not a pressurized tank. As such, the surface of the tank, point A, and the free stream of the flow down here, F, the pressure would be 0. They're both exposed to atmosphere, and they're not confined by any type of a boundary. So pressure at these sections would be 0. So when the fluid at a reference point is exposed to the atmosphere, the pressure is 0, and the pressure head term can be cancelled from Bernoulli's equation. So anywhere in this equation, we can equate any of these terms to 0. We would cancel them out, and so on. V sub A would also be 0 because surface of the tank, there would be no velocity associated with the water. In that case, that would cancel out too. So I'm going to skip a few of these. The velocity head at the surface of the tank in a reservoir is also considered to be 0, and it can be cancelled out from the Bernoulli's equation. From point B to E, from this point, go up to C, C to D, and D to E. This is inside the pipe. It has a uniform flow area. There's no change in the cross-sectional area of the pipe. Under these conditions, the velocity will remain the same. There's no change here in velocity. So when there are 2 points of reference for Bernoulli's equation, they're both inside a pipe of the same size. No other forms of energy would be taken out or added. Those previous assumptions would be still valid. And then the velocity head terms, in this case, on both sides of the equations would be equal, and they would be cancelled out. So what about the reference points on the same level? What can we say about those? Well, when the 2 points of reference are both at the same elevation, then the terms Z1 and Z2, they would be equal. We can cancel them out. Remember, they were addition terms, and when we add the same term, equal terms, to 2 sides of the equation, we can easily subtract them from 2 sides of the equation because they are the same. And that's what we do in this case. What about the Venturi meters and other closed systems with unknown velocities? What we can say about that, a figure that's shown here is a Venturi meter. It can be used to measure the velocity of a flow, as we discussed previously in a fluid flow system. In subsequent chapters of the book, if you're interested, you can read about those. But again, if you want to analyze such a device, we are going to apply the principles of Bernoulli's equation. Anywhere we have a reduced diameter, we would adjust it accordingly. If we don't, and then we don't need to make the modifications as I discussed previously. So the reduced diameter section of B causes the velocity of flow to increase with a corresponding decrease in pressure, right? We discussed that as we are reducing the diameter of the section, we're increasing the pressure. And it's important to realize it. Let me shortly talk about Torricelli's theorem and go over that with you. This is based on observations and experimental data. When we have a flow with certain velocity and it flows from a siphon, of course that flow would depend on the elevation difference between the free surface of the fluid and the outlet point. In this case, that is point 2. So this is point 1 up here. This is going to be point 2. So fluid is flowing from, again, one side to the other through a smooth rounded nozzle. If we want to calculate the velocity of the flow at point 2, we would write the Bernoulli's equation out. And of course, we need to consider the change in the elevations when we assume a reference point. So the reference point would be the reference point. It would be on the surface point 1 and point 2. So we write it between these two. The difference would be we assume a distance h or a height h in that case. So let's see how we can write the equation and derive the equations. P1 and P2 is 0. One is the point where the point inside the tank, not pressurized, a point inside a non-pressurized tank, and the point outside of the nozzle. So pressure at 1 and 2 would be the same. It is at 0, so this term is going to cancel out as shown here. This term is going to cancel out as such, and this term v sub 1 squared divided by 2g is going to cancel out because at point 1 v is also 0. That's the surface. There's no velocity associated with that. We have the velocity down here. So the remaining terms would be z sub 1, z sub 2, and v sub 2 squared divided by 2g. Okay. So we're going to solve for v sub 2. As such, we get this term up here, this equation. Let's see what we can do with the terms under the radical here, and that is z sub 1 minus z sub 2. We already made the assumptions. That would be an h. So v sub 2 would be square root of 2gh. And that is called the Torricelli's theorem in honor of Mr. Torricelli. Discovered this, observed this back in 1645. I would challenge anybody that was born in 1645 and listening to these lectures, right? We can apply Torricelli's theorem, expand it, keep the system as such that you can see, except you're going to change the nozzle, and we try to measure the jump in this case. Again, we apply the same type of a principle, and we can easily calculate the jump itself. What would be the velocity at point 2, and how far would that take us? What would be the h in this case? I want you to go through this and actually solve it and try to understand it on your own and get back to me with any questions that you might have. So let me take a look at an example here. Ignore the number, just call it example problem, please. We have a system as such. This is similar to the previous system. We are going to compute the required air pressure above the water to cause the jet to rise 40 feet from the nozzle. That's a really long distance for the water jump or water rise, and we assume h is 6 foot. Okay, so let's set up Bernoulli's equation to obtain an expression for the velocity of flow from the nozzle as a function of the air pressure, P sub 1 divided by gamma 1 plus Z sub 1. These terms at V1, the velocity is 0. At point 2, pressure is 0, right? At point 1, it's the air pressure. This is under pressure. In this case, we can see that the pressure of the air in this case. So we keep the term P sub 1, we keep Z sub 1. These other terms they drop out. We keep Z sub 2, and we keep V sub 2 squared divided by 2G. All the non-zero terms, of course, stays within the equation. From here, we would calculate V sub 2. This is simple algebra, really. We take the square root of 2G multiplied by P sub 1 by gamma plus Z1 minus Z2. We can take the term Z2 on the other side, Z1 minus Z2, into an algebraic manipulation to get that, knowing that H would be Z1 minus Z sub 1 minus Z sub 2. That would be replaced by H. Okay, so we are down to V2, V sub 2 would be square root of 2GH in this case. This is similar to the Torricelli's theorem, as you've seen previously, and as such, we know the terms. In this case, the height is 40 feet, so this is known. Gamma is, in this case, we actually do know the gamma that is given in this case, because the problem asked for gamma of the water, right? This was water, right? Exactly. This is a water, so we know the gamma of water is given in the problem. So I had to go back and come forward again with this. So the 40 feet is the rise. It's the desired rise. H is given, gamma is given. All we really need to do here is we'll do a numerical substitution and calculate P sub 1 as 14.73 psi G. Let's take a look at a falling head. Let's solve a fluid flow due to a falling head. Okay, so let me go through these, and when we discuss the falling head, of course, we are talking about diameter of the pipe down here. The pressure is not going to be 0 anymore at this point. It is under pressure of the fluid, and we use some integration. What we do is we would actually take a strip of the height of the tank. We call that D sub H, and we would actually calculate the time that's required for the fluid level to fall from H1, depth H1 up here. This is again a strip of the fluid down to a depth of H2. Okay, we calculate that time by going back at this equation and actually do that. Again, these are not that trivial at first, but let me go back and take a closer look at the falling head in this case. All right, so let's take a closer look at the system in this case. We would like to develop a method for computing the time that's required to empty a tank. We are going to take a look at the velocity, of course, realizing that the velocity would there would be a variation in the velocity as the depth decreases. And this image that's shown here, we have a well-rounded nozzle in the bottom. and the fluid actually discharges from that particular nozzle at a given depth of fluid h. We call that velocity, according to Torricelli's theorem, we call that V sub j. J stands for jet. The volume flow rate through the nozzle, as we've discussed previously, could be A. It is A multiplied by the velocity, so A sub j by V sub j. That is in the unit of cubic meter per second or cubic feet per second. In a small amount, during if we want to take a look at a small fraction of a time, we call that d sub t. You want to see how much discharge we are going to have through that nozzle. We have q, a sub j times b sub j, multiplied by a fraction of a second. Could be 0.001 second or 0.01 seconds, and so on. So we call that dt, right? Don't be scared by all these terminology here. dt is nothing but a fraction of the time in which we want to measure the discharge from the nozzle at the bottom of this tank. So we simply need to multiply discharge because it's cubic meter per second. We need to multiply it by that time, and that could be a millisecond, could be 0.001 seconds, what have you. Of course, as we are doing this, there would be fluid leaving the tank, and the level of the fluid would be decreasing. So during a small time increment dt, the fluid level drops a small distance dh. So we measure that. The discharge would be whatever that it will be at that fraction of the time at dt. And then during that dt, there will be the volume or the volume flowing would be equal to dh, because that's the amount that it drops. Of course, that would be multiplied by the volume of the tank in 3D, but we make some assumptions here. Again, during this small time increment dt, the fluid level drops a small distance dh, and the volume of the fluid removed from the tank, in that case, would be a sub t times d sub h, right? We know the cross-sectional area of the tank multiplied by the small discharge that is converted into height of the tank, then we're going to have minus a times d sub h, minus showing that it is a discharge, right? So if we have a sub j, v sub j dt, that must be equal to a sub t d sub h. This is calculating q from one method. This is calculating the q from the other methods. They're the same q, so they're equal. So if we solve for the time dt, we can calculate the dt from this equation as what you see here. Again, simple algebra. We go from here to this equation down here, and now we're going to apply Torricelli's theorem. V sub j here, we are going to substitute for this v sub j, and we are going to substitute that by the square root of 2gh. So simply from this equation, now we're going down to this equation. All we did was we substitute v sub j by square root of 2gh as shown down here, right? And then in order to do more manipulation, we would write d sub h out in terms of h. Again, we are rearranging the equation in this case, okay? There would be no h here, actually. This should be divided by 2g, because we already took the h out. H is to the power half, we take it to the numerator from the denominator that was under the radical under the square root, and it's going to be h to the power minus 1 d sub h. So there's a typo here. So just cross this little h out, please. And then we are going to expand this, knowing that the d sub t would be as shown up here. As we calculated previously, we need to expand this d sub t over the entire discharge, and that, of course, we need to sum that up, and as a result we need to use the integral as a summation from t sub 1 t sub 2 of d sub t. What we do in this case is, because the term that doesn't have h, again, this should not be here, can be treated as a constant. We take those out, take it to behind the integral right here, and we take the integral from h1 to h2. That is the equivalence here. We just simply take the integral of both sides. Okay, on the left hand side we take it with respect to t. On the right hand side we take it with respect to h. And this would be constant. We take that to the behind the integral, and we take the integral here, as you can see, and of course the integral on the left hand side would be t2 minus t1, and of course we, after taking the integral, we do more manipulation, and that would take us to this equation that you can see here, h to the power half 1. This could also be considered square root of h1 minus square root of h2. Okay, so we're going to use this equation to compute the time required to drain a tank from h1 to h2. Let's take a look at this example problem. Okay, so for the tank shown in the image below, find the time required to drain the tank from a level of 0.3 meter to 0.5 meter. The tank has a diameter of 1.5 meter and a nozzle has a diameter of 50 meter. Okay, so let me get my tools back here. There you go. Okay, so T2 minus T1, we have the equation. We have a sub t, we have a sub j. We can calculate these two, and of course we are going to substitute a sub t and a sub j in that equation. Again, we take the ratio as it's shown here, a sub t over a sub j. That ratio is 900. The equation is still shown up here, so I can carry that forward. So we're going to substitute that by 900. G is known, a sub 1 is known, a sub 2 is known, and we simply calculate T2 minus T1 as 417 seconds. Divide that by 60, it's going to be 6 minutes and 57 seconds, right? Pretty straightforward example. That brings me to the end of the slides. As always, if you have any questions, send them my way through the course website. Let learning continue. I hope you find these lectures useful in your studying. Thank you.